Welcome to the deep dive. You sent us these university-level chemistry lecture notes
Mm-hmm.
about stoichiometry,
Right?
and we're going to try to unpack them for you.
Yeah.
I know chemistry might not sound like the most fun thing at first,
It can be a little daunting.
but trust me, this stuff gets really interesting
talking
once
about.
you see how it all
Well,
works.
it's fascinating.
Yeah, so we're going to try to equip you with a clear understanding of stoichiometry, even if you don't have like a background in chemistry.
Right.
So let's just jump right in. What is this thing? What is stoichiometry?
So stoichiometry is all about the quantitative relationships between substances and chemical reactions.
Okay.
What's fascinating here is how stoichiometry gives us a way to measure and predict the amounts of reactants and products involved in any chemical reaction.
Oh, wow. So it's not just like a theoretical thing, it's like an actual practical thing.
Very practical. Yeah.
So this isn't just about passing a chemistry test. This is like applicable in the real world.
Absolutely.
Okay, so if we were to look at like a chemical reaction like this example from the notes,
Right.
2 hydrogen molecules plus 1 oxygen molecule makes 2 water molecules.
Yep. That's a classic.
Can you break that down for us, and how does that relate to stoichiometry?
Well, so in that equation, you have your reactants, the hydrogen and the oxygen, and your product, the water.
Hmm.
And the stoichiometry tells us the exact ratio in which they react and the amount of product we'll get.
I see.
So for every 2 molecules of hydrogen, we need 1 molecule of oxygen to get 2 molecules of water.
Okay, that makes sense.
And we can scale that up to any amount.
So it's like a chemist's recipe.
Exactly like a recipe.
So, if I'm baking a cake, I need to know exactly how much flour and sugar and eggs I need,
Right.
and the recipe gives me those proportions.
Precisely. And stoichiometry does the same thing for chemical reactions.
But here's where I start to get a little lost, because we're dealing with atoms and molecules, things we can't even see.
Right.
How on earth do you measure something that small?
That's where this brilliant concept of the mole comes in.
Okay.
It's like the central unit in stoichiometry.
Okay.
The mole is a huge number, 6.02 times 10 to the 23rd power, to be exact.
Wow.
And it's also known as Avogadro's number.
Okay, so just like a dozen is 12.
Exactly.
A mole is this giant number.
Precisely.
So a mole of anything is 6.02 times 10 to the 23rd of those things.
Yeah, atoms, molecules, whatever we're dealing with.
Okay, now the notes mention different types of things, like atoms, molecules, ion pairs.
Yeah.
Can you kind of break those down for us? What are the differences?
So an atom is the most basic unit of an element,
Okay,
like a single carbon atom.
got it.
A molecule is formed when 2 or more atoms bond together.
Okay,
So like water, H2O, that's a molecule.
okay, so 2 hydrogens and 1 oxygen
Exactly.
make a water molecule.
Right.
And then what was the other one? Ion pairs?
Ion pairs form when oppositely charged ions are attracted to each other,
Okay,
like in table salt, sodium chloride.
okay.
That's an ion pair.
So we've got these tiny little particles that we can measure using the mole, but how do we actually know how much a mole of something weighs?
Right. So we can't exactly put a single molecule on a scale.
Yeah, that would be pretty tough.
So that's where relative mass and molar mass come into play.
Okay.
We use a relative mass scale
Huh.
because individual atoms are just way too small to weigh directly.
So is that kind of like when we measure things in like tons versus ounces or something?
It's similar, yeah.
We need like a different scale for different things.
Yeah, exactly. It's like comparing the weight of a feather to the weight of an elephant.
Okay, I get it.
We need a different scale.
Yeah.
And we use carbon-12 as our reference point.
Okay.
It's kind of our gold standard.
Okay, so all the other atoms are compared to carbon-12.
Exactly, and that gives us relative atomic mass.
Okay, and then molar mass.
Molar mass is simply the mass of 1 mole of a substance,
Okay.
expressed in grams per mole or mola.
Okay, so if we had like a mole of sugar,
Right.
how much would that weigh?
So to figure that out, we'd need to look up the relative atomic masses of all the elements in sugar,
Okay.
carbon, hydrogen, and oxygen.
Mm-hmm.
And we'd add those up, taking into account how many of each atom are in the molecule.
Okay.
So sugar, or sucrose, is C12H22011.
So 12 carbons, 22 hydrogens, 11 oxygens.
You got it.
Wow, that
Yeah.
seems like a lot to calculate.
It can be, but once you get the hang of it, it's pretty straightforward.
So in the end, how much would a mole of sugar weigh?
A mole of sugar would weigh 342 grams.
Okay, so that's like a can of soda.
Yeah, about that much.
Wow. So we've got the mole, which is how we count these tiny particles,
Right.
and we've got molar mass, which tells us how much a mole weighs.
Exactly.
Now, how do we actually like convert back and forth between grams, something we can measure, and moles, this giant number?
That's a great question, and luckily there's a really handy equation for that.
Okay.
Moles equals mass divided by molar mass.
Okay.
So if we know the mass of a substance and its molar mass, we can calculate how many moles we have.
And if we know the number of moles and the molar mass,
Right, yeah.
we can work out the mass.
Exactly.
So it's like a two-way street.
It is, yeah. It connects what we can measure in the lab with the world of molecules.
Okay, my mind is officially blown. This is way cooler than I ever thought chemistry could be. But before we move on to like chemical equations and stuff, I'm curious about something else the notes mentioned.
Okay.
Chemical formulas.
Yeah.
There's like different types.
There are.
Molecular, empirical, structural.
Right.
What are the differences between those?
So think of it like levels of detail.
Okay.
The molecular formula tells us the exact composition of a molecule.
Okay.
So it lists all the elements and how many atoms of each are present.
Okay.
The empirical formula gives us the simplest ratio of elements.
Okay, so it's like a simplified version.
Exactly.
Okay.
And then the structural formula shows us how the atoms are actually connected in the molecule.
Oh, cool.
It's like a 3D model.
Okay, can we do an example of that? Like something that I might encounter in my real life?
Sure. So let's take ethanol,
Okay.
the stuff that gives wine its kick.
Oh, yeah.
So the molecular formula is C2H6O.
Okay, so that means it has 2 carbon atoms,
Yes.
6 hydrogen atoms,
Uh-huh.
and 1 oxygen atom.
Exactly.
Okay.
Now, the empirical formula would be CH3O.
Okay, so that's the simplest ratio.
Right, because we can divide all the subscripts by 2.
Oh, I see. Okay.
And then the structural formula would show you how those atoms are bonded together.
Okay, so it's like a blueprint. The
Exactly.
molecular formula is like the list of ingredients. The empirical formula is like the simplified list.
Yep.
And the structural formula is like the actual instructions for how to put it together.
That's a great analogy.
Okay. I'm starting to feel like I'm getting a handle on this.
Great.
This is really cool. So we've kind of laid the groundwork here with like atoms and molecules and moles and all that stuff.
Yeah, the basics.
But I'm eager to dive into the actual like chemical reactions.
Right. And how we use all this information to figure stuff out.
Absolutely. And that's what we'll get into next time.
All right, so buckle up, folks. Things are about to get really interesting.
Definitely.
Okay, so we've got a good grasp on like moles and molar mass and all that.
Right. Building blocks.
But how do we actually use all that to like track what's happening during a chemical reaction?
That's where balancing chemical equations comes in.
Okay.
It's all about the law of conservation of mass.
Okay.
Matter can't just like magically appear or disappear out of nowhere.
Right, so it's got to go somewhere.
Exactly what goes in must come out.
So it's kind of like a perfectly balanced equation.
Exactly. It's like a seesaw.
Everything needs to be equal on both sides.
Precisely. We need to make sure that the number of atoms of each element on the reactant side, the stuff you start with, matches the number of atoms on the product side.
Okay, so what you end up with.
Right.
So we can't just like throw a bunch of chemicals together and hope for the best?
Well, sometimes you can.
No. But in general, yeah, you want to make sure everything is accounted for.
Okay, so how do we do that? How do we balance these equations?
So we use coefficients.
Okay.
Those are the numbers you see in front of the chemical formulas.
Okay.
And they tell us how many molecules of each substance are involved.
Okay.
But we can't change the subscripts, those little numbers within the formulas.
Right, those are like baked in.
They are.
You can't mess with those.
Okay. Changing those would be like trying to turn water into hydrogen peroxide just by adding an extra oxygen.
That's not going to work.
Not going to happen.
Okay, so let's look at an example.
Okay.
Like that hydrogen and oxygen making water one.
Yeah. So if we just write it as H2 plus O2 makes H2O,
Okay.
that's not balanced.
Okay, why not?
Because on the left side, we have 2 hydrogen atoms and 2 oxygen atoms.
Okay.
But on the right side, we only have 1 oxygen atom.
So we're missing an oxygen.
We need to balance that out.
Okay, so we need to add a coefficient.
We do.
Okay.
So if we put a 2 in front of the water molecule,
So 2H2O.
yeah, now we have 2 oxygen atoms on both sides.
Okay. But now we have 4 hydrogens on the right side.
You got it.
And only 2 on the left.
Right. We need to fix that too.
So our seesaw's out of balance again.
It is.
Okay, so what do we do?
We add a 2 in front of the hydrogen molecule on the left.
Okay.
So now the equation becomes 2H2 plus O2 makes 2H2O.
Okay, and now we have 4 hydrogens and 2 oxygens on both sides.
Exactly. Everything is balanced.
Awesome. Okay, so now our equation's all nice and balanced.
It is.
But how do we actually use this in practice? The notes mention something called stoichiometric calculations.
Right.
And honestly, that just sounds kind of scary.
It's not as bad as it sounds, I promise.
Okay, good.
Once you have a balanced equation, you can use it to figure out all sorts of things.
Like what?
Like how many grams of product you'll get from a certain amount of reactant,
Oh, okay.
or how much of each reactant you need
All right.
to make a certain amount of product.
Oh, that's pretty cool.
It's like having a recipe for your reaction.
Okay, so you know what you want to make.
Right.
You know what you need to start with.
Mm-hmm. And the balanced equation tells you the exact proportions.
Okay, so it's like a roadmap for your chemical reaction.
That's a great way to put it.
You know where you're starting, where you want to end up,
Right.
and how to get there.
Exactly.
Okay, cool. So can we look at like a specific example?
Absolutely. Let's look at the Haber process.
What's that?
It's how we make ammonia,
Oh, okay.
which is super important for fertilizer.
Oh, wow. So this is like real world stuff.
Very real world.
Yeah.
So the balanced equation for the Haber process is N2 plus 3H2 makes 2NH3.
Okay, so 1 nitrogen molecule plus 3 hydrogen molecules makes 2 ammonia molecules.
You got it.
Okay.
So those coefficients tell us the mole ratios,
Okay.
the proportions in which the substances react.
So for every 1 mole of nitrogen,
Yes.
we need 3 moles of hydrogen to make 2 moles of ammonia.
Exactly.
Okay, so it's like a recipe.
It is.
Where you got to have the right amounts of each ingredient.
Precisely.
Okay, cool. So what if we had like 2 moles of nitrogen and plenty of hydrogen?
Okay.
How many moles of ammonia could we make?
So if 1 mole of nitrogen makes 2 moles of ammonia,
Yeah.
then 2 moles of nitrogen would make 4 moles of ammonia.
Oh, okay. So you just double it.
Yeah, you just scale it up.
Okay, cool. What if we had 6 moles of hydrogen and like tons of nitrogen?
Okay, so the ratio of hydrogen to ammonia is 3 to 2.
Okay.
So 6 moles of hydrogen would make 4 moles of ammonia.
Okay. So you double the hydrogen, you double the ammonia.
Exactly.
Okay, I'm starting to get this.
Great.
So we're using the mole ratios from the balanced equation
Right.
to figure out how much product we can make.
Uh-huh.
But what if we want to work with grams instead of mole?
We could totally do that. We just need to use molar mass to convert back and forth.
Right, because grams is something we could actually measure.
Exactly.
Okay, so it's like a 2-step process.
Yep.
We convert grams to moles using molar mass,
Uh-huh.
then use the mole ratios to figure out the amount of product or reactant. Right.
And convert back to grams if we need to.
Exactly. It all comes full circle.
This is so cool. It's like chemistry has become a math problem.
It kind of is, yeah.
Okay, but what about reactions that happen in solutions?
Good question.
Like when we dissolve stuff in water,
right.
the notes mention something called molarity.
Molarity is a way to express the concentration of a solution.
Okay.
It tells us how many moles of solute, the stuff that gets dissolved, are in 1 liter of solution.
Okay, so it's like how strong the solution is.
Exactly.
Like if I make iced tea,
right.
the more tea mix I add, the stronger it is.
Precisely, the more concentrated it is.
So a higher molarity means a stronger solution.
Exactly.
Okay, and there's an equation for calculating molarity, right?
There is?
Molarity equals moles of solute divided by volume of solution in liters.
That's it.
Okay, so if I know how much solute I have and its molar mass, I can figure out the moles.
Yep.
And then if I know the volume of the solution, I can calculate the molarity.
Okay, cool. So let's do an example.
Right.
What if we dissolve like 175.32 grams of table salt in 2 liters of water?
Okay.
What would the molarity of that solution be?
All right, so first we need the molar mass of sodium chloride.
Okay, that's 58.44 grams per mole.
Right.
So we divide the mass by the molar mass to get the number of moles.
Yep.
Which is 3.
3 moles of sodium chloride.
Then we divide that by the volume.
Just 2 liters.
So the molarity is 1.5 m?
Exactly. 1.5 molar.
Wow. I'm feeling like a real chemist now. This is awesome.
Told you it wasn't that scary.
I know, right? So we can use molarity to figure out the concentration of solutions.
Yes.
Which is like super useful in all sorts of situations.
Absolutely.
Like in a lab or even just in everyday life.
Yeah, like think about medications.
Oh, yeah.
The dosage is really important.
Yeah, you don't want to take too much or too little.
Exactly. And molarity helps ensure you're getting the right amount.
Wow, that's pretty important.
It is.
So molarity is like another tool in our chemistry toolbox.
It is a very important one.
Okay, cool. Now, the notes also mention diluting solutions,
Right.
which is basically like making them weaker.
Yeah, less concentrated.
Okay, so there's an equation for that too.
There is. It's M1V1 equals M2V2.
Okay, what do all those letters stand for?
So M1 is the initial molarity.
Okay.
V1 is the initial volume.
Okay.
M2 is the final molarity.
Okay.
And V2 is the final volume.
Okay. So if I wanted to dilute a solution, I could use this equation to figure out how much water to add?
Exactly.
Okay, that makes sense. And the notes also say to be careful when diluting acids.
Oh, yeah. Always add acid to water.
Yeah.
Not the other way around.
Got it. Safety first.
Absolutely.
We don't want any explosions.
No, we don't.
Okay, cool. So we've talked about balancing equations, molarity, dilutions.
Yeah.
What else is there?
Well, there's one more fascinating concept from the notes we should touch on.
Okay.
Avogadro's law.
Ooh, that sounds important.
It's all about gases, and it states that equal volumes of any gas at the same temperature and pressure
Okay.
contain the same number of moles.
Whoa. So no matter what the gas is,
Right?
if the temperature and pressure are the same,
Yep.
then the same volume will have the same number of moles.
Exactly.
That's kind of wild.
It is, but it makes sense when you think about it on a molecular level.
Okay. How so?
Well, gases are mostly empty space,
Okay.
with molecules just zipping around all over the place.
Okay.
So at the same temperature and pressure, the average space occupied by a molecule of one gas is about the same as the space occupied by a molecule of a different gas.
Oh, I see.
It's a pretty simple principle.
Okay. And the notes mention molar volume, too.
Right, molar volume is just the volume occupied by 1 mole of any gas
Okay.
at a specific temperature and pressure.
Okay.
At standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere of pressure,
Okay.
the molar volume of any gas is 22.4 liters.
Okay, so that means 1 mole of any gas at STP takes up 22.4 liters of space. So if we know the volume of a gas at STP, we can figure out how many moles we have.
Right, you just divide the volume by 22.4.
Oh, that's easy.
It is, and it works the other way, too.
Okay.
If you know the number of moles, you can calculate the volume.
Okay, so it's like all these different ways of connecting the dots.
Exactly. We can go from grams to moles to volume.
Oh, wow. This is so cool. So we've gone from balancing equations to molarity to Avogadro's law.
Yeah, we've covered a lot of ground.
And it all kind of ties back to the mole.
It does.
It really is like the central unit in all of this.
It's the foundation of Stoichiometry.
Wow. Okay. My brain is officially full.
I bet.
This is amazing, though. I feel like I actually understand stoichiometry now.
That's great to hear.
It's way less scary than I thought it would be.
Glad to hear it.
But before we wrap up, is there anything else from the notes that we should touch on?
Yeah, there's a couple more things we should talk about.
So we've covered like balancing equations and molarity and all kinds of stuff.
We have. We've really delved into the heart of stoichiometry.
I know. I feel like I'm starting to see the world in moles and grams now.
That's the goal, to develop that stoichiometric intuition.
Yeah. It's pretty cool to see how it all connects.
It is. It's a beautifully interconnected system.
And the thing that I'm really starting to appreciate is that it's not just about like theoretical calculations. This
Right.
stuff has actual real world applications.
Oh, absolutely. Countless applications in so many different fields.
Like what?
Well, think about medicine,
Okay.
developing new drugs and figuring out the right dosages.
That makes sense.
Or agriculture,
Okay.
optimizing the use of fertilizers to get the best crop yields.
And then that all ties back to that Haber process we talked about.
Exactly.
Wow. So stoichiometry is like secretly running the world.
It kind of is. It's the foundation for so many things we take for granted.
It's like the silent hero of chemistry.
I like that, the silent hero.
This deep dive has really opened my eyes to how important this stuff is.
I'm glad to hear that that's what we aim for, to make these complex concepts accessible and engaging.
Well, you've definitely succeeded. I feel like I have a much better grasp on stoichiometry now.
And that's the power of learning.
It's like you've given me a new superpower.
The power of stoichiometry.
Exactly. I can see the world in a whole new way now.
And that's what we hope for, that you'll leave this deep dive with a sense of wonder and a desire to learn more.
I definitely will, and I hope our listeners will too.
Me too.
So for everyone out there, keep exploring the fascinating world of chemistry and never stop asking questions.
Absolutely.
Until next time, happy